Dear friends, today we are going to discuss some basic mineralogical characteristics of acid, igneous and alkaline rocks. In the following sections, we will discuss number 1, introduction of acid igneous rocks, followed by mineralogical characteristics of acid igneous rocks, chemistry of acid igneous rocks, alkaline rocks, mineralogical property of alkaline rocks, chemistry of alkaline rocks and conclusion. Acid igneous rocks refer to the light color, low specific gravity and high silicate minerals rocks. Acid igneous rocks in general contain more than 63% of silica with K feldspar and also contain acid plagioclase and mineral quartz. The minerals are grouped in several ways according to their relative importance to the rock mass. Essential or primary minerals like quartz, mica and feldspar in granite, or whose presence gives name to a specific rock type. For example, rebecite, microgranite. Accessory minerals may be present but have no bearing on the rock type. For example, zircon, apatite in granites. Secondary minerals are produced by lateral weathering or hydrothermal alteration of the original essential minerals. For example, kaolin from the alteration of feldspars in granite, or chloride from the hydrothermal alteration of primary ferromagnesian minerals. The minerals are in 6 main groups starting from the feldspar or feldspathoids, amphiboles, pyroxenes, micas, olivines and oxides of silicon and metals. The lighter colored minerals are termed as felsic, the darker ferromagnesian as mafic. The relative proportions roughly determining the color of the rock, hence the acid igneous rocks which have a high felsic content are generally paler than the basic types with higher mafic minerals. Rock types include granite, granodiorite and their volcanic equivalents, rhyolite and dacite. Dacite and granodiorite may contain slightly more than more darker iron and magnesium-rich minerals such as biotite and amphibole than granite and rhyolitic minerals. Acidic melt can be generated at depths as low as 35 kilometers. Acid igneous rocks are characterized by the presence of quartz, orthoclase, plagioclase and various accessory minerals. Granite and granodiorite are rich in quartz, but in quartz diorite to diorite, the amount of quartz gradually diminishes to 0. From granite to diorite, the proportional amount of orthoclase diminishes while that of plagioclase increases. The accessory minerals are often biotite and hornblende. The biotite occurring mostly at the granite end, the hornblende at diorite end of the series. Pyroxenes are comparatively rare. In normal granite type, there is always a subordinate quantity of plagioclase, usually oligoclase. In alkali granite, this mineral disappears and mafic minerals like aegirine and rebecite appears, giving rise to aegirine granite and rebecite granite. Normal granites are named according to the most prominent accessory minerals like muscovite, biotite, hornblende or augite granite. In hornblende granite, the principal minerals are perthite, elbite, quartz and hornblende. Perthite is probably due to exsolution modified by introduction or redistribution of elbite. There is a little biotite, magnetite, fluorite and sphene, and the accessory minerals found is the amphibole. In biotite granite, the coarse quartz and perthite grains are surrounded by mosaic of elbite. There is abundant sphene and the presence of the biotite In Rapa-Kivi granite, quartz, sodic plagioclase, perthite, biotite and fluorite are the major minerals. Plagioclase rims on the perthite grains are characteristics of this rock. Fluorite is indicated by 3 intersecting cleavage lines. In hypersthene granite, the quartz, perthite, hypersthene and magnetite are the major minerals. The granite family is by far the largest division of the plutonic rocks, for it comprises all rocks of deep-seated origin with over 66% of silica and is a common rock type. In general terms, the members of this family may be characterized as consisting of a holocrystalline and, as a rule, coarsely crystalline aggregate of quartz, 2 or more feldspars and 1 or more varieties of mica, hornblende and augite. The feldspars can be recognized by their color and cleavage. Frequently, the orthoclase is colored fresh color or red, while the soda lime feldspar is usually white. The quartz is recognized by its glassy luster and conchoidal fracture. It is usually white or smoky gray in color and is found in irregular grains filling up the interstices between the other minerals. The mica, which may be either muscovite or biotite, is to be recognized by its cleavage. Accessory minerals are numerous, including apatite, zircon, sphene, orthite, rutile, garnet, topaz, cordierite, cassiterite, tourmaline, fluorite, molybdenite, hematite, magnetite and iron pyrites. Minerals resulting from the decomposition of the original constituents and especially of the feldspars are cerussite, talc, kaolin, epidote, calcite, chlorite and serpentine. With increase in the proportion of plagioclase relative to the orthoclase, granite passes to granodiorite. There may be also a slight diminution in the amount of quartz and an augmentation of the mafic constituent. When the two feldspar occur in approximately equal quantity, the term adamelite is used. Similarly, tonalite is used for granodiorite, in which the plagioclase is greatly in excess of the orthoclase. Quartz diorites differ from the granodiorite in containing the much smaller amount of quartz. Otherwise, they are very similar to the tonalites, with the practical disappearance of quartz and orthoclase. The series ends with diorite. The essential minerals in dacite are quartz phenocryst. In addition to this, usually some tridymite and cristobalite, alkali feldspar, glass and minor accessories are present. Rhyolite is the volcanic equivalent of granite. It exhibits the same mineral as granite embedded in an abundant glassy or cryptocrystalline ground mass, which is frequently flow banded. The cryptocrystalline components are often feebly developed or absent. The extremely glassy modification of the rhyolite is the pure black glass known as obsidian. Many pit stones too are of the rhyolitic composition and are distinguished by their pitch-like luster. Rhyolite, which carry a notable proportion of soda lime, plagioclase and are thus equivalent to the adamelite variety of granodiorite, are called as delenite. Some types of the rhyolites are the volcanic equivalents of soda granite and carry phenocrysts of soda orthoclase or anorthoclase and crystals of soda pyroxene and soda amphiboles, indicating their alkalic characters. Komendite is an alkali rhyolite with aegirine, erfedsonite and rebecite. Pantellerite is distinguished by presence of anorthoclase with aegirine augite and triclinic alkali amphibole causserite. In some rhyolites, the sole porphyritic constituent is a soda feldspar having the same glassy habit as potash feldspar, that is sanidine, According to the predominance of potash feldspar or soda feldspar, the rhyolites may be divided into potash rhyolites and soda rhyolites. The latter comprise the more acid pentellurites. Fluxion structures is often shown in the ground mass by the beautiful wavy lines of flow which sweep round the large embedded grains. The same structure is also occasionally brought out under the microscope by the strict parallelism of the feldspar microlites or by bands of crystallites and trichstein, the glassy rhyolites and the obsidians. The quartz latites and rhyodikites are invariably porphyritic with phenocrysts of plagioclase, sanidine, anorthoclase and rarely orthoclase and perthite, and ferromagnesians, hornblende or biotite. Occasionally diopside. The quartz is rounded and are doubly terminated pyramidal crystals without prismatic faces. The plagioclase phenocrysts are often zoned and some of the biotites and hornblendes are surrounded by reaction rims, as is common in andesites. Hornblende is sometimes the brown basaltic type, but ordinary green amphiboles are also found. The chemical composition of the plutonic acid igneous rocks from quartz diorite through granite are close to those of the alkaline volcanic rocks. Plutonic rocks of the orogenic batholiths and continental interiors differ from siliceous differentiates of other environments primarily in greater contents of potassium and other large ion lithophile components. Those with enough potassium to have subequal amount of plagioclase and potash feldspar can be assigned to high potassium series, of which lattices and quartz lattices are the most common volcanic members. In this respect, felsic continental rocks differ from plagiogranite of oceanic environment and ophiolites. The latter lack the potassium feldspar that is so conspicuous in their alkaline equivalents, usually referred to broadly as trondhjemites. They are also common in ancient continental shields, island arcs and other regions of thin crust. Most granitic rocks can be assigned either to S-type derived from sedimentary or metasedimentary source rocks or I-type produced by melting rocks that are dominantly igneous. The most conspicuous compositional differences are in their alumina concentrations of certain trace elements inherited from their sources, like continental trondhjemite granites produced by melting of sedimentary rocks have more alumina that can be accommodated in feldspars. The excess is expressed as normative corundum. The I-type has a normative diopside. The former is also richer in transition metals and in several lithophile elements such as barium, rubidium, thorium and light REE. The alkaline rocks are those which contain in their chemistry alkalis like potassium oxide and sodium oxide in great enough for alkaline minerals to form. Such minerals may be unusually sodium rich with a relatively high ratio of alkalis to silica SiO2 as in the feldspathoids. Other alkaline minerals have high ratio of alkalis to alumina, that is Al2O3, as in aegirine pyroxene and the sodic amphibole rebecite. Alkaline igneous rocks crystallize from magma derived by small degree partial melting of ultramafic rocks, mostly peridotites, in the Earth's upper mantle. Some types of kimberlite contain the so-called ultra-deep diamonds, that is, diamonds hosting inclusions of minerals stable at pressures above 13 gigapascals and may potentially descend from melts generated in the transition zone or even in the lower mantle. Small melt to rock ratios derive enrichment of alkaline magmas in alkalis and trace elements incompatible with respect to the mantle rocks. Certain alkaline magmas have chemistries too unusual to be accounted for by melting of unmodified peridotite, for example, contain high potassium, barium or carbon dioxide contents. Their sources are believed to have been modified, that is metasomatized, by melts or fluids rising from yet deeper levels in the mantle. The driving forces behind mantle metasomatism are not very well understood. Possible sources of metasomatic melts or fluids include mantle plumes, subducted oceanic crust and a delaminated subcontinental lithosphere. During their ascent from the mantle, alkaline magmas evolve, that is, their chemical composition, physical properties like density, dynamic viscosity, etc., and solid to liquid ratio change in response to the changes in pressure, temperature, composition of the surrounding rocks, etc. Alkaline magmas may undergo crystal fractionation, thermogravitational diffusion, liquid immiscibility and other processes that will produce derivative magmas quite distinct from primary or initial magma. Alkali rocks are divided into three groups according to silicon content: ultrabasic rocks, isolites and unites, that is 40 to 45% of silica, gabbroid rocks, rhyolites and exoxides 45 to 50%, and cyanitic rocks, alkali cyanides and nepheline cyanides more than 50% of silica. In the Earth's crust, alkali rocks are found chiefly in small to 50 to 100 square kilometers intrusive bodies of nepheline cyanides and alkali cyanides or their effusive varieties, that is nephelinites, phonolites, leucitites and tephrites within volcanic alkali basaltic associations on the continents and oceanic islands. Isolites and meltigites are typical of complex alkali ultrabasic massifs where pyroxenites and olivinites predominate. Major carbonatite deposits have been identified in these massifs. The nepheline cyanides are divided into muscite, in which potassium and sodium together are less than aluminium, and the rarer agapite, in which potassium and sodium together are more than aluminium. Various minerals rich in zircon, titanium, niobium and strontium are typical of agapeitic rocks. Alkaline igneous rocks are those with an excess of alkali metals, that is Na2O plus K2O over silica. Rocks undersaturated with alkali metals are known as subalkaline. Alkaline rocks are relatively rare. However, they exhibit significant variation in mineralogy and therefore comprise a larger number of rock types. Many alkaline rocks are silica undersaturated and contain feldspathoid mineral, mainly nepheline and leucite. Many also contain alkali feldspar. They can, however, be silica saturated and oversaturated also. A subset of alkaline rocks are potassic or ultrapotassic, such as kimberlites, lamproites and sponsonites. In exoxides, the plagioclase in labradorite are more basic. It is characterized by the zone plagioclase. The range of composition may be from basic labradorite to oligoclase. The plagioclase often is corroded and replaced to some extent by alkali feldspar, feldspathoids and especially by analcite when present. The rhyolite barium orthoclase is the dominant feldspar. The principal ferromagnesians are augite, olivine, alkaline hornblende such as barkevicite, rebekite, erfurtsonite and biotite. The proportions of minerals vary considerably in a same rock type. In the orthoclase gabbros, however, normal augite and hornblende are the rule. The augites are commonly zoned and may be displayed in hourglass structure. Hypothesis is rare. The alkaline minerals include soda, orthoclase, perthite, nepheline, sodalite, horite, and nosinite. Analcite takes the place of feldspathoids in teskinite. Accessory minerals which are often unusually abundant in the alkaline rocks include apatite, sphene, magnetite, and ilmenite. Depending on the proportion of minerals, they range from leucocratic nephelinites consisting of nepheline and only minor amounts of pyroxene to melanocratic pyroxenite. Nepheline is the dominating felsic mineral. Leucite is being much common, whereas titaniferous augite or azurine augite is the most important mafic component. The Jacobirangites contain only minor amounts of nepheline but are composed chiefly of a bright green azurine augite rimmed with purple titaniferous augite and intergrown with differing amounts of magnetite, ilmenite, biotite, melanite, olivine, calcite, apatite, barkevicite, perovskite, pyrite, and zeolite. Some other varieties contains melilite and other as wollastonite. In nepheline cyanides, the feldspar are found generally as major constituents like microcline perthite, orthoclase and orthoclase perthite, albite and oligoclase. In few nepheline cyanides, cryptoperthite and anorthoclase are the principal feldspars. Andesine and labradorite are the typical feldspar of nepheline diorites and theralites. Orthoclase and perthite orthoclases are frequently dusted with fine-grained clay mineral and finely divided iron oxide, and this alteration is therefore visible as a distinct redding of the feldspar. Zoning is visible in some orthoclases, particularly when porphyritic. Perthite intergrowths range from vague cryptoperthites to be well-defined exsolution textures, but are usually considerably modified by replacement by albite. In some varieties, this replacement is so extensive as virtually to eliminate the potash feldspar so that albite becomes the predominant feldspar. In phonolite, the nepheline which characterizes it occurs in the form of phenocryst as hexagonal cross section and rectangular longitudinal sections of interstitial to feldspar in the matrix. But a wide variety of other mafic minerals are characteristics of alkaline rocks. Iolites are characteristically sodic. They grade into a corresponding group of potassic rocks of more gabbroic composition, are known as exoxides. Like iolites, the latter contain abundant nepheline, but it is accompanied by potash feldspar, and titaniferous augite and amphibole are more characteristics than azurine. Exoxides are found in many of the same clusters of the igneous complexes as iolites, but they are more commonly associated with and gradational into plagioclase bearing rocks of more common gabbroic and syenitic type. Alkaline rocks are found in a wide range of tectonic environments, but are particularly common in ocean islands and continental rifts. The occurrence of alkaline rocks can be extrusive or intrusive. Extrusive alkaline rocks comprise both lavas and pyroclastic rocks formed by accumulation of ejecta from explosive eruptions. Alkaline parental magmas generally originate by melting of the mantle rocks at smaller degrees of partial melting or greater depths than subalkaline magmas. Based on total alkali silica diagram, the rocks are classified as alkaline basalts, picrites, tephrites, and trachybasalts. They generally plot within the alkaline fields and chemically distinct from Martian meteorite. These rocks are iron rich and fairly silica poor. generally have a higher L2O3 and Na2O content. During their ascent from the mantle, alkaline magmas evolve, that is, their chemical composition, physical properties including density, dynamic viscosity, etc., and solid to liquid ratio change in response to changes in pressure, temperature, composition of the surrounding rocks, etc. Alkaline magmas may undergo crystal fractionation, thermogravitational diffusion, liquid immiscibility, and other processes that will produce derivative magmas quite distinct from the primary or initial magma. For example, the astonishing diversity of alkaline igneous rocks exposed at Lovozero, that is Kola, Russia, can almost all be traced to the same type of parental magma. This is not to say, of course, that this 650 km² layer cake of nepheline and syenites and phonolites crystallized from a single blob of phonolytic melt. Quite to the contrary, there may have been as many as 6 or more discrete intrusive phases, each with its own trace element budget and isotope signature. The earliest products of magma differentiation may not be what comes to mind when you think of alkali-rich rocks. Thermogravitational diffusion and fractionation of MgFe silicates gives rise to ultramafic rocks just like the ones produced from other magma types, for example, tholeiitic basalts. A careful study of mineral composition, melt and fluid inclusions and whole rock trace element geochemistry will be needed to recognize the alkaline affinity of these rocks. Acid igneous rocks in general contain more than 63% of silica with K feldspar and also contain acid plagioclase and mineral quartz. Acid igneous rocks refer to light color, low specific gravity and high silica rich rocks. The chemical composition of the plutonic acid igneous rocks range from quartz diorite through granites are close to those of alkaline volcanic rocks. Plutonic rocks of orogenic batholiths and continental interiors differ from siliceous differentiates of other environments, primarily in a greater contents of potassium and other large iron lithophile components. Rock types includes granite, granodiorite and their volcanic equivalents, rhyolite and dacite. Most granitic rocks can be assigned to either to S-type derived from sedimentary or metasedimentary source rocks or I-type produced by melting rocks that are dominantly igneous. The most conspicuous compositional differences are in their alumina concentrations of certain trace elements inherited from their sources. The alkaline rocks are those which contain in their chemistry alkalis like potassium oxide and sodium oxide in great amount for alkaline minerals to form. Alkaline igneous rocks are those with an excess of alkali metals, Na2O plus K2O over silica. Rocks undersaturated with alkali metals are known as subalkaline. Alkaline rocks are relatively rare, however, they exhibit significant variation in mineralogy and therefore comprise a large number of rock types. During their ascent from the mantle, alkaline magmas evolve, that is, their chemical composition, physical properties including density, dynamic viscosity, etc., and solid to liquid ratio change in response to changes in pressure, temperature, composition of the surrounding rocks, etc. Alkaline magmas may undergo crystal fractionation, thermogravitational diffusion, liquid immiscibility and other processes that will produce derivative magmas quite distinct from the primary or initial magma. Thank you very much.